my today's lesson, and today I just want to actually talk about how questions get tackled in as far as redox titration is concerned. If you have been very keen and as well following my videos, I've actually been able to tackle questions revolving around direct titration, questions revolving around back titration, and today I just want to focus on redox titration. And of course, the word redox comes from two different words that have different meanings, and of course that is actually reduction and oxidation. So that actually means reduction and oxidation. So we have reduction and oxidation. So I'll say reduction and I'll say oxidation. So the two come together to form a word called redox. Redox has been discussed widely in Form 1 work in as far as our Kenyan system is concerned, the 844 system of education. And this actually revolves around trying to understand what really means by this term reduction. So in this case, you might have magnesium, for example, getting reacted with copper 2 oxide. In this case, magnesium is a gray metal and copper 2 oxide is actually a black solid. When this reaction has to actually end up occurring, we shall always have to go back to our reactivity series and be able to know that pastors say church members are cursing Zion. I think let's have church servants getting protected. So pastors say church members are cursing Zion. I think let's have church servants getting protected. Of course, this is potassium with a chemical formula capital K, that is sodium with chemical formula Na, that is calcium capital C small a, magnesium capital M small g, aluminium capital S small l. We have carbon capital C, we have zinc capital Z small n, we have iron capital F small e, we have tin capital S small n as the chemical formula. Then we have what we call lead capital P small b, we have hydrogen capital H, we have copper capital C small u, we have silver capital S small g, we have gold capital A small u, we have platinum capital P small t. That is how we actually end up coming up with what we call a reactivity series. So looking at this, you'll realize that copper is below magnesium. Now, if you want to interpret actually this reactivity series, you should understand that potassium becomes the most reactive and platinum becomes the least reactive. In that case, as I go down the reactivity series, the rate of reaction decreases. So that means if I compare magnesium and copper, magnesium becomes most reactive. Copper becomes now the least reactive if they're actually found in a reactivity series only consisting this part and this part. So that means if I have to come from this point up to this end, then I can say magnesium becomes the most reactive, copper becomes the least reactive. But now in as far as this reactivity series is concerned, we always say potassium is the most reactive and platinum is the least reactive. Good. And of course, you should note that between copper and silver, we have mercury, whose chemical formula is capital H small g. So mercury is actually more reactive than silver, but less reactive than copper. Okay, that is mercury, capital H small g. Now coming back here, I'll realize that now copper being more reactive than hydrogen, in this case here, but less reactive than magnesium, makes it possible for it to get displaced from its oxide. So magnesium is more reactive than copper. So that means it has a high ability of displacing copper from its oxide. So magnesium will displace copper from its oxide. What are we going to get? We are going to get magnesium oxide. That means the magnesium picks the oxygen. Good. Then it forms magnesium oxide. Then the copper becomes displaced. Look at this. So that means magnesium has taken the oxygen from copper, it being more reactive than copper. So it becomes oxidized. It is actually oxidized. To get oxidized means oxygen has actually ended up getting added onto it. So it gives us the magnesium oxide. The copper has been displaced. It was copper oxide or copper to oxide. It ends up now forming copper metal. That means the copper to oxide has undergone reduction. So magnesium has picked the oxygen to undergo oxidation, or it has been oxidized. So it undergoes oxidation, or it has been oxidized. Then the copper loses the oxygen to magnesium. It ends up getting reduced. So it undergoes reduction, or now it is actually reduced. Good. So oxidation, reduction, reduction, oxidation, redox, redox reaction. That can be a very good example of a redox reaction. If you go to form, we will always say reduction means the gaining of electrons. So we have reduction, then we have oxidation. That is under a topic called electrochemistry. So in electrochemistry, we will always say reduction is the gaining of electrons. Good. And oxidation is the losing of electrons. Good. Here, reduction can actually end up having what we call a decrease in oxidation state. A decrease in oxidation state, then there is actually an increase in oxidation state. Let me give a practical example. If I have zinc 2 ions, this 2 positive means the oxidation number or the oxidation state. That tells us that this metal, of course because of the positive charge, because all metals are cations or positively charged particles, has actually lost, because positive in chemistry means losing, so it has lost 2 electrons. So if it gains the 2 electrons, what do we form? We are going to form the zinc metal. Look at that. So it actually forms the zinc metal. Now if I come here and say copper, then I actually take this arrow to this point, then I write here copper 2 ions plus 2 electrons. You see, it was a metal, you see, but now it has actually lost 2 electrons. So it forms copper 2 ions. Look at that example. If I look at this, I'll realize that here there is the gaining of electrons. You see? So if there's the gaining, of course positive means gaining. If I say I'm going to give you 10 shillings, you have gained. So I'll say plus. Whatever you have plus, what I've given you. So it has gained, because you're saying plus. Look at that. So it has gained 2 electrons. So that means obviously here, if there's gaining of electrons, we obviously call that process reduction. You see? And in that case, there is a decrease in the oxidation state or oxidation number. Let's look at this. The oxidation number here is 2 positive. The oxidation number here is 0. Look at that. From 2 positive to 0, the oxidation number decreases. So obviously it is a reduction if it has to be written like this. Why is it a reduction? 1, there is the gaining of electrons. 2, a decrease in the oxidation number. Okay, let's come back here. The oxidation number here is 0. Okay, the oxidation number here is 2 positive. Practically, I'm actually using these examples just like the way they are actually written to be able to explain to you how reduction and oxidation can get differentiated. So the oxidation number or state here is 0. The oxidation number or state here is 2. So there's an increase in the oxidation number. Increase in the oxidation number. So that means this undergoes oxidation. And again, it has lost 2 electrons. The copper metal has lost 2 electrons to form copper 2 ions. Okay. Don't mind about which one has undergone reduction or oxidation as far as the way they are actually arranged in the reactivity series, but I actually want you to understand that reduction means gaining of electrons and oxidation means losing of electrons. There's actually a decrease in the oxidation state or number and increase in the oxidation state or number. Okay, so if I have to go to what we call redox titration, of course you'll actually understand that, for example, reduction, oxidation are actually some of these processes that actually occur in as far as all electrochemical cells are actually concerned. For example, we'll always say reduction has to actually occur at that point where the less reactive metal is actually located. Oxidation has to occur where the most reactive metal is actually located. For example, oxidation can occur at the cathode and reduction can occur at the anode. Good. And of course, a cathode will mean a negative electrode in an electrochemical cell or a half cell. Then the anode will mean the positive electrode in an electrochemical cell or a half cell. So cathode, then anode. Cathode, then anode. So cathode oxidation, anode reduction. So in redox titration, I want to use an example that we can be able to get in as far as knowing how we can do the calculations in relation to how a redox titration can get done. So redox titration. I was first explaining to you the meaning of redox to mean reduction and oxidation, and when redox titration gets done in as far as form 3 work is concerned and the topic called the mole, then you're supposed to understand that you need to have at least 2 reagents. You need to have 2 reagents in as far as our practical work is concerned. So we'll have what we call, for example, potassium manganate 7. Then you can have an ammonium ion 2 salt. Ammonium ion 2 salt. With 6 molecules of water of crystallization. So ammonium ion 2 sulfate salt or ammonium ion 2 salt. Look at this. So this is KIMNO4, potassium manganate 7. And if potassium manganate 7 is actually absent, you can also use potassium dichromate 6. Good. So you can either use potassium manganate 7 or potassium dichromate 6. Why do we say manganate 7 and yet it's 4? If you go to the same topic called electrochemistry in form 4, you'll understand that there's something actually called oxidation numbers or oxidation states. If you do actually the calculations, you'll realize that the oxidation state of manganese ions in this case is actually 7. So we say potassium manganate 7. Potassium dichromate 6. So the oxidation state of the chromium ions in this case will be 6. So you say potassium dichromate 6. Ammonium ion 2 sulfate salt. So if these ones get used in redox titrations, they need first to actually get acidified. Why do they need to get acidified? To ensure that the process of oxidizing whatever they have to oxidize occurs completely, because these oxidizing agents have the highest ability of oxidizing this salt, this ammonium ion 2. So the ammonium ion 2 salt will get oxidized to ammonium ion 3. Look at that. So the ammonium ion 2 gets oxidized to ammonium. Why do we say ammonium ion 2? Look at this number here. So ammonium ion 2. That means ion is a metal in this compound. You see, has an oxidation number or state of 2. So we actually call this compound ammonium ion 2. Now, I've said these are oxidizing agents. They have to get acidified. For example, you can add few drops to these oxidizing agents before they can get used in this experiment. You can add few drops of potassium, or you can actually be able to use few drops of concentrated sulfuric acid. And in this case, if you are oxidizing potassium manganate 7 or potassium dichromate 6, you have to actually use very concentrated acids. So you can add a few drops of concentrated sulfuric acid to acidify the oxidizing agents containing potassium. Good. So they can now get used in the oxidizing of this other reagent completely, because they have actually ended up getting acidified. Now let me use this practical example. For example, in this potassium manganate 7, we have manganate 7 ions. The manganate 7 ions are actually able to give this potassium manganate 7 its purple color or appearance. And in this case, the manganate 7 ions are able to actually lose 5 electrons to end up forming manganese 2 ions. So the purple manganate 7 ions are reduced to the colorless manganese 2 ions. The purple manganate 7 ions are reduced to the colorless manganese 2 ions. Then if I'm using this, I'll probably have the dichromate 6 ions. These ones are actually responsible for the orange appearance of potassium dichromate 6. So the orange color of the potassium dichromate 6 is brought about by the chromate 6 ions, the dichromate 6 ions, which are actually orange in appearance. So in this case, I can come here and be able to say the chromium 6 ions will lose 3 electrons to end up forming the chromium 3 ions. Good. The color changes from orange to green. The change from orange to green will actually demand that you don't use any indicator in as far as this titration process is concerned. So they'll ask you in the examination, why do you think in redox titration no indicator, no commercial indicator, no universal indicator is used at the end of the day like phenolphthalein or methyl orange? It's because when the oxidizing agents are used and they have been well acidified by adding a few drops of an acid like sulfuric acid or sulfuric 6 acid, they actually end up just changing in color. So for example, the purple color disappears to form a colorless what? Solution. The orange color disappears to form a green solution. The change in color will completely tell us that the reaction has come to an end. So no indicator can be used to show the end point of a reaction. Now I'll use a practical example to be able to actually explain this, and this is what I'm going to use. Let me say, for example, I have potassium manganate 7 as my oxidizing agent and the ammonium ion 2 salt. Good. And I may say, for example, in this case, that I'm going to actually use this one as my data as far as getting the right answer in this case is concerned. This one is potassium manganate 7 and this is ammonium ion 2 sulfate salt. These two are actually able to have something of this sort, MnO4 minus plus ion 2. You only pick the ion 2 and leave the remaining part of that compound when you're writing the ionic equation. And we can say plus H positive. So the MnO4, the ionic part of that compound, Fe2 plus, because actually ammonium ion 2 sulfate is also ion 2, the ionic part of that compound. Then H positive tells us that the oxidizing agents had been acidified, because the presence of hydrogen ions in a compound will tell us more about the acidity of that substance. Very good. An acid must have hydrogen ions as the only positively charged ions. So what happens here? These manganate 7 ions will oxidize ion 2 ions to ion 3 ions. Good. Then after oxidizing these, so oxidize, this to iron 3 ions. See? So if it oxidizes this to iron 3 ions, it gets reduced. And in chemistry, an oxidizing agent undergoes reduction, or it gets reduced. So it gets reduced to manganese 2 ions. Very good. Then plus, this oxidizing agent will also oxidize the hydrogen to form water. So look at this. The manganate 7 ions will oxidize iron 2 to iron 3. So iron 2 ions are actually able to give us a green precipitate or color. Then iron 3 ions will give us what we call a brown precipitate. So the color changes from green to brown to tell us that the iron 2 ions, which are green in appearance, and as far as that precipitate is concerned, will get oxidized by this oxidizing agent to iron 3 ions, which are brown in appearance, and as far as that precipitate is concerned. Then I've said the manganate 7 ions being able to oxidize this iron 2 will make them to end up getting reduced to manganese 2. So the color changes from purple, good, to colorless. So that means the manganate 7 ions are purple and they actually get reduced to manganese 2, which will make them to become colorless. Then I'm also saying the manganate 7 ions, being the oxidizing agent, will also oxidize the hydrogen ions that got brought from the acid to actually give us water, because H plus O is water. Oxidizing means adding oxygen. Okay, and of course, how many electrons have been lost? I've told you in this case here that the manganate 7 ions lose 5 electrons to form manganese 2, so 5 electrons. Good. So that means in that case, the electrons lost by the manganate 7 are to be gained by the iron 2. So we shall put here 5, then we shall put here 5 to balance the equation. Okay. Iron 2 ions, that means these are the electrons lost, you see. So that means the manganate 7 ions will pick the 2. So I'm picking 2 for us actually to balance the equation. Also put here 2. Then we have 2 manganese, 8 oxygen atoms. We shall put here 8 to balance the equation. So how many hydrogen atoms are here? 16. Good. So 8 oxygen atoms, then 16 hydrogen atoms. So it's just very easy. You just put here 16 to balance the equation. That one gets done. As easy as that. Or you can decide to actually say, if this is not actually to be included here, we can put here 8. Then you can put here 4 to make your work easier. Why? Because you have 4 here to mean the oxygen atoms. Then you can put here 4 to mean that 4 oxygen atoms are present. Then how many hydrogen atoms are here? 8. So you can just put here 8. Then you balance the equation. Very good. So we'll end up having 4 oxygen atoms. Then if you put here 4, oxygen ends up having 4. Then 8 hydrogen atoms, 8 hydrogen atoms. So that is 4 times 2. So that is what you're supposed to. And in as far as calculating the moles is concerned, it's very easy. Just use the mole ratio of 1 to 5. Then you can be able to get the moles of any compound as far as this part is concerned. Now, I'm assuming I'm actually using the same oxidizing agent, that is scheme 4, and a dibasic acid. Dibasic acid means an acid with 2 hydrogen atoms. Di means 2. Dibasic acid. So with an X here with 2 molecules of water of crystallization. Then I'm trying to assume that in this case, for my work to be easier, in as far as the calculations are concerned, I can end up having, for example, 5 grams of this dibasic acid, of course getting dissolved in 1 liter of the solution. So 5 grams getting dissolved in 1000 centimeters cubic of this solution. then maybe we use like 31.75 centimeters cubic of this solution in our titration, and then maybe here, or we can decide to actually lower this to 25. So we can say if this 31.75 we can come here and say we have 0.0125 molar as the concentration, and we may have here, let's use here 25 centimeters cubic, and we can use here 31.75 centimeters cubic. Good. And we can probably say maybe the reacting ratio is 2 to 5. Good. Maybe the first question can be, so I'm actually trying to look at that aspect of ending up getting the value of X, which can actually give us what we call an exact molar mass of what X can stand for in as far as this basic acid is concerned. So I have actually to ensure that the values I'm going to use are actually going to give me the exact value. So in this case, I can say maybe calculate the moles of CuMnO4 that reacted. So I'm going to have this CuMnO4. This capital M tells us that these moles are found in 1,000. So what about 31.75? So 0.0125 moles, because of this capital M, are obviously found in 1,000 centimeters cubic. This is called molarity. Then what about 31.75? What will be the answer? So this will obviously be 0.0125 times 31.75 divided by 1,000. So it will be 0.000397. Good. For the purposes of accuracy, I can have all those decimal places. So I have 0.000397 moles. These are the moles of the oxidizing agent that reacted in that titration. Then maybe number 2, I can say moles of the dibasic acid that actually reacted. Good. So I'm going to say the mole ratio is 2 to 5. And remember, the moles of CuMnO4 that reacted are this. So I can come and write this value here. Why? Because the CuMnO4. Good. So I'm going to have here 0.000397. So these moles are equivalent to 2 as far as the mole ratio is concerned. What about 5? I'm going to say 2 represents this. What will 5 represent? I'll get the moles of the basic acid that reacted. 0.000397. What about 5? Good. So I'll just cross multiply. So I'll have so good. That's the point. So I can say answer times 5 and divide by 2. So I'm going to get 0.00099. Good. So I'll have 0.00099. How do I get this? I'll say 5 times 0.000397 divided by 2. So it must give me this. So these are the moles of the acid that reacted. So if 2 represents this, then 5 represents this. So 0.00099 moles. Okay. I can get the molarity of the dibasic acid. So molarity of the acid. And of course, molarity means the moles in 1,000 centimeters cubic. The moles in 1,000. The moles in 1,000. So I'll come here and say that was used was 25. So this volume that got used must contain the moles that reacted. What about 1000? So the volume that got used was 25, and the volume that got used must be containing the moles that reacted. So that means these moles are found in 25. What will 1000 meters cubic contain? That gives us the molarity. Molarity means the moles in 1000. And these moles are the ones that reacted, and this is the volume that actually got used. So we'll come here and say 0.00099 are the moles that reacted, and they are actually found in 25 centimeters cubic that got used. What will 1000 centimeters cubic contain? For us to get the molarity.